Hi and good day Dr. Dzulkarnain and Dr. Azizu. My name is Jing Yan and this video is presented by Group 37. In this video, we are going to talk about our plant design project, which is given the title Biogas and Biofertilizer Production from Palm Oil Mill Effluent Pomade. The presentation is divided into 7 parts: Introduction, Literature Review, Conceptual Process Design, Heat Integration, Process Control and Instrumentation, Hazard Study, and lastly, conclusion. First, introduction. Malaysia is known as the second largest palm oil producer in the world, after Indonesia. The palm oil plantation encloses 5.8 million hectares of Malaysia land. The production covers 11% of oils and fats production in the world and 27% of export trade of oils and fats. Pomade is actually come from the full name Palm Oil Mill Effluent. It is an untreated liquid waste that contains high concentration of organic nitrogen, phosphorus, and different supplement substances. It is poison to the environment because of its high COD and BOD. The problem statement of our project is the increase of the palm oil production leads to the fact that the formation of pomade is increasing too. Therefore, in our project, we are aimed to design a plant to convert pomade into the two profitable products, which are biogas and biofertilizer. The objectives of our projects includes conducting market study for both the products, biogas and biofertilizer, choosing an optimal location for plant construction, study and determine the most economic and practical process to produce the products, perform mass balance manually, develop a sensible PFD and PNID, conduct heat integration, implement process control, execute hazard study, and design a reasonable and safety-first plant layout. Lastly, our project is also aimed to determine the feasibility of the proposed plant and maximize the recovery of the process too.
Good morning everyone, my name is Huong Yu Zhe, matrix ID of 23688, and I'll be doing the literature review and hazard analysis for this project presentation. So firstly, for the physical and chemical properties of the feed, which is the pomade. The pomade is a thick, brownish colloidal mixture, consists of water, oil, and fine suspended particles. Pomade is quite high in temperature, which is 80 to 90 degrees Celsius. And as what you can see in the table below, pomade has a pH value of 4.5, which is slightly acidic due to the acids present in the pomade. And pomade is high in BOD and COD amount due to the organic materials present in the pomade. And same goes to the suspended solid, nitrogen, and oil present in the pomade. Okay. Besides that, pomade also contains a lot of macro and micro elements such as phosphorus, potassium, magnesium, calcium, boron, iron, manganese, copper, zinc, and etc. Pomade can be broken down into a few major elements, which are carbon with the concentration of 47.7%, which is the highest, and followed by the oxygen 38%, and hydrogen, nitrogen, sulfur, and others. Okay, next will be the physical and chemical properties of the products, in this case, which are biogas and fertilizer. So biogas or biomethane is a mixture of gases produced by organic materials. And these biogas compositions are methane with 60 to 75 volume percentage, and followed by carbon dioxide with 19 to 33 volume percentage, and nitrogen, oxygen, and water. For the biofertilizer instead, biofertilizer produced from pomade is oily, blackish, and have an earthy smell. And this biofertilizer basically is the treated pomade sludge, contain pH value of around 8.5, carbon percentage of 25.5, nitrogen of 4, oxygen of 7, and moisture content of 75%. And it consists of the composition of phosphorus with less than 1 milligram per liter, potassium, magnesium, and calcium, iron, manganese, copper, and zinc. The composition of calcium and ferrule will be more than 1 milligram per liter, which is allowable limit.
Hi, I'm Dinesha from Group 37, and I'll be presenting on the market study, the plant location selection, as well as the economic evaluation. So first, let's take a look at the market study, in which I'll cover the world demand as well as the projected demand. So let's take a look at the world demand first. As we can see in the data and plot of the graph, that the growth in palm oil production in 2017 is topped by the two palm oil producers, the major producers, which will be Indonesia at 54% and Malaysia at 32%. And as we can see, both the countries have expended 85 to 90% of the total palm oil production demand across the world, followed by Thailand, Colombia, Nigeria, and others. So, as we can see in Malaysia itself, the demand has been 21 million megatons. So, next we take a look at the capacity of biogas in megawatts. So, in this source by Statista, where the biogas energy capacity in Malaysia from 2009 to 2019 have been studied, we can see that it has been gradually increasing from 2009 to 2015. And then you can see a very sharp increase from 2015 to 2019, which is from 36 megawatts up to 135 megawatts. So with this world demand, we can clearly make a projected demand. So firstly, let's take a look at a statement by Minister for Energy and Environment of Malaysia, Ms. Yeo Bee Yin, where she said 20% covered by renewable energy by the year 2025 and 2% of its electricity by exploiting renewable sources. And as we know, total renewable energy capacity of biogas and biomass is predicted to increase by 50% by the year 2020. So, because of this, we have set the consumption of biogas at 270 megawatts in the year 2020 in our 10-year demand projection demand. So, based on the CEDA report, we can see that the increment of renewable energy is predicted to be at 6.8%. So because of that, we have taken the basis of 7% annual increment for our 10-year demand projection. So this is our envisaged demand for biogas from 2020 to 2030 with 7% increment assumption. So in 2020, it's expected to be 270 megawatts, and by the end of 2030, it will be 531 megawatts. So next, we will be looking at the plant location. So we have compared 4 locations and chosen Bukit Mertajam Penang, which is near the Veolia water tank, as our location. So the factors that were considered before making this decision would be the raw material availability, the water supply, the energy availability, markets, waste disposal, site characteristics, transportation facilities, labor supply, community factors, and climate. So the 4 locations that we have compared will be the Mukim Bera Pahang, which is near the Heavies Biogas Power Plant 1. The location 2 is Bukit Mertajam Penang, which is near Veolia Water Tank. Location 3 is Sri Jelutong Pahang, which is near the Sri Jelutong Biogas Power Plant. And the last location will be Pantai Remes, which is at Perak, and which is near the Pantai Remes Biogas Power Plant. So as we can see over here, after taking these factors into consideration, location 2 has scored the most points. So the reason why raw material availability was given the highest point, highest multiplication factor, is because it's very important for us to get source of our raw material, which will be palm. So as we can see, Penang has the highest source for palm, followed by
Assalamualaikum and hello, my name is Abdul Wafiy, and now we'll proceed with the conceptual process design. So I will start with the process screening. The first one is heuristic approach of CH4 production. So there are 2 sequences of alternative for anaerobic digestion. The first sequence is 2 reactors in parallel, and another sequence is 2 reactors in series. So our choice of reactor arrangement will be 2 reactors in series or sequence 2, as it has high efficiency of palmate digestion, which can reach above 70%. So better biogas production and palmate treatment can be achieved. So the diagram below shows the block diagram of sequence 2 process. Next one is the heuristic approach of CH4 purification. So there are three main components of gases in this process, which is methane, carbon dioxide, and hydrogen sulfide, which is labeled as A, B, and C. And there are three alternatives or sequence for CH4 purification. And our choice of sequence will be sequence 1, where we separate C or H2S first from the methane and carbon dioxide, and then proceed with another separation process where we will separate methane from the carbon dioxide. So alternative 1 is chosen because the most harmful components must be removed first from the biogas. So H2S should be removed first from the streamline, as it is extremely toxic and acidic gas, which can cause serious corrosion on the surface of the equipment and seriously reduce the product quality. So this is the first diagram is the block diagram of sequence 1 for purification process, and another diagram is the block diagram for the combined overall sequence chosen. Next is transition screening. So these are the alternatives for reactor, where we have CSTR, UASB, and AF. So our choice of reactor for the first stage or mesophilic digestion will be UASB, and for the second stage or thermophilic digestion, it will be CSTR. So these reactors are chosen because they have high efficiency for their respective digestion process. The next one is alternative for separator, where we have adsorption, membrane, and serogenic. And our choice of a separator will be adsorption, as it has high efficiency and has lower cost compared to other alternatives. So this is the summary of the chosen equipment as discussed previously. That's all for me for this part. Thank you.
Hi, now I'll be presenting on the potential economic analysis. So to calculate the economic potential analysis, first we have to calculate the price of raw materials. So the raw materials for our project would be water and palm. So we calculated for per annum, which has totaled up to 1,181,339 ringgit Malaysia and 28 cents. Next, the revenue is calculated based on the products, which would be methane, biofertilizer, carbon dioxide, and biogas production. So in order to calculate the price per annum, we first have to get the price for per metric ton in ringgit Malaysia, and then to calculate the production per year, which is the metric ton per annum. So we have assumed 275 days of production and 22 hours daily, which has totaled up to 63,116,912 ringgit Malaysia and 44 cents. Next, to take a look at the utility cost, we have taken into account the electricity tariffs and the water tariffs. So first we have to calculate the unit per year, and then to calculate the price per unit, which in total, price per annum has totaled up to 32,434,129 ringgit Malaysia and 23 cents. So, with all this information, we can calculate the economic potential 1, which only takes into account the revenue and the raw materials, and the EP2, which takes into account the revenue, raw materials, as well as the utilities. So the EP1, which is revenue minus raw material, has summed up to 61,935,573 ringgit Malaysia and 16 cents for per annum. And for EP2, taking revenue minus raw materials and utilities, has cost us RM 29,501,443 ringgit Malaysia and 93 cents per annum. Next, it is also important to take into account the capex and also the opex. So as for the capex, which will be the capital expenditure, will be divided into two different costs, which will be the fixed capital cost as well as its working capital. So as for the fixed capital cost under capex would be the design and other engineering and construction supervision, all the equipment items and the installation, all the piping, instrumentation and control systems for our plant, the buildings and structures, as well as the auxiliary facilities such as the utilities, land and civil engineering work. Next will be the working capital, which takes into account the startup cost, the initial catalyst charges, the raw materials and intermediates in the process, the finished product inventories, as well as the funds to cover outstanding accounts from customers. Next, as for the operating expense, which will be the OPEX, would take into account two different costs, which would be the fixed cost and also the variable cost. So what is fixed cost? Fixed costs are costs that are unaffected by the company's volume. So the plant's capacity will not affect the cost on this. This will be, for example, the rent, the insurance, as well as the equipment. Next will be the variable cost. This is directly linked to the company's volume as for how much of capacity of biogas and biofertilizer we are producing. So these, of course, the examples would be the raw materials, the commissions for the employees, as well as the shipping costs. So we have calculated the operating expense for our project. So first we will take a look at the land price. So our land has now been focused in Penang. So it will be 8 ringgit 50 cents for per meter in rural area of Penang with an annual interest rate of 5%. So next will be the three major equipments, which will be the UASB, the CSTR reactor, and also the MDA scrubber. So the USB equipment cost is 3,821,759 ringgit Malaysia. And to calculate for the major equipment CSTR reactor, we first have to get the cost constant, which will be not changing, of course, 129,332, and with the formula of CE equivalent to CSN, we calculate the total equipment cost, which sums up to 246,203 ringgit Malaysia and 36 cents. And lastly, for the MDR scrubber, the equipment cost is 625,800.
Hello and Assalamualaikum. My name is Mohammad Faizal bin Mohammad Fauzi. For my part, I will explain to you about our overall process flow sheeting based on mass balance calculation. As what had been explained earlier, our process consists of two anaerobic digester which arranged in series and connected with gas purification part, which consists of two amine scrubber together with stripper. While for our biofertilizer production, we use dryer to dry the sludge from anaerobic digester. Therefore, based on our mass balance, we have decided to mix a total of 5,000 kg per hour of pomade with 4,506 kg per hour of water in order to produce a total of 52% of pomade and 48% of water. The mixture were fed into the first reactor with 90% conversion of biogas. From the first reactor, we obtained a total of 5,262 kg per hour of biogas, while the remaining digestate were fed into the second reactor. As for the second reactor, with the same conversion of 90% production of biogas, we had obtained a total of 526 kg per hour of biogas. The total of biogas from the first and second reactor were fed into the first amine scrubber with a together with a total of 1,000 kg per hour of amine solution, with absorption efficiency of 90% of methane and carbon dioxide. Therefore, our treated gas from first amine scrubber produced were 5,348 kg per hour, while the bottom part of the scrubber were fed into stripper for absorption process of amine solution. Okay, next, the treated gas from first scrubber were fed into the second amine scrubber with a total of and produced a total of 1,542 kg per hour with 97% purity of product methane, while the bottom part were fed into the stripper to produce a total of 3,768 kg per hour with 99% purity of carbon dioxide. Okay, lastly, the digestate from second anaerobic reactor were fed into the dryer to remove a total of 95% of water and produce a total of 50 kg per hour of biofertilizer. So that's all for our process flow sheeting.
Next, I will proceed with the heat integration part of our project. By inserting all the information and the stream data into the hint software and setting the minimum temperature difference delta T min as 10 degrees Celsius, we are able to obtain the composite curve from the software. The composite curve shows the area of process-to-process heat transfer, the minimum cold and hot utilities required for the process. In our design, the minimum cold utilities required QC min is 5,785 kilowatt, while the minimum hot utilities required QH min is 0 kilowatt. Next, problem table algorithm PTA is generated to find the pinch temperature of our process. From the cascade, three important informations are shown. They are the pinch temperature, QH min, as well as QC min. Later, a heat exchanger network HEN is designed by using the hint software tool. Based on the process flow diagram, before the heat integration, our plants require 3 heaters and 7 coolers to complete the process. However, after the heat integration, 3 heat exchangers are added to the process to replace the heaters. With the addition of the heat exchangers, the heat flow of the cold utilities are able to reduce too.
Assalamualaikum and hello, I'm Wafiy and now we'll proceed with the process control and instrumentation. So I will start with the process control strategy. The first equipment is the reactor, which is one of the major equipment. So there are 3 control objectives for this equipment. Note that the major variable that we use is based on our control objective. For example, our first control objective is to maintain the temperature of the reactor, and the measured variable that we use is the temperature of the reactor itself. So this is applied to all control objectives for all equipment. For the first control objective, the manipulated variable is the heat duty of the heater at inlet stream, and the type of controller used is feedback controller. The next one is to maintain the level of pomade in the digester, and the manipulated variable is the control valve opening of inlet flow of pomade, and the type of controller used is feedback controller. The last one is to maintain the pressure of the reactor, and the manipulated variable is the valve opening of the gas outlet, and the type of controller used is feed-forward controller. The next one is also the major equipment, which is absorber. There are also 3 control objectives for this equipment. The first one is to maintain the pressure of the absorber column, and the manipulated variable is the control valve opening of the gas outlet stream, and the type of controller used is feed-forward controller. The next one is to maintain the inlet temperature of the absorbent into absorber. The manipulated variable is the heat duty of the heater at inlet stream of the absorber, and the type of controller used is feedback controller. And the last one is to maintain the level of liquid absorbent in the absorber column. And the manipulated variable is the control valve opening of the liquid absorbent outlet stream, and the type of controller used is feed-forward controller. And this one is also the major equipment, which is stripper. It has similar control objective as absorber. The only difference is the equipment used, which is the stripper use heat exchanger instead of heater. So the difference is at the manipulated variable, which is the control valve opening of heating stream of the heat exchanger instead of heat duty of heater. The next one is minor equipment, which is clarifier. So the control objective is to maintain the sludge level in the clarifier, and the manipulated variable is the opening of the control valve of sludge outlet stream, and the type of controller used is feed-forward controller. The next one is also the minor equipment, which is reboiler, with the control objective of to maintain the temperature of absorber solution in the reboiler, and the manipulated variable is the opening of control valve of the inlet steam supply, and the type of controller used is feedback controller. The last one is the mixer, which have the control objective of to maintain the flow rate of 2 different feed streams in the mixer, and the manipulated variable is the opening of control valve for inlet flow of water and pomade, and the type of controller used is ratio controller. With the control strategy, we come up with this overall PNID, which is the combination of the major equipment and minor equipment. That's all from me for this part. Thank you.
Alright then, for the heads-up study, there are 5 NOCs in total that are being studied, which are NOC 1, storage tank, NOC 2, mixer, NOC 3, heat exchangers, NOC 4, reactors, NOC 5, scrubber and strippers. But in this project presentation, I'll be discussing only about the NOC 1, which is storage tank of format and water. So there will be 4 parameters to be discussed in NOC 1, which are flow, temperature, pressure and level. The guideworks used are less, no, more, low and high. So for example, there is less flow of liquid from the tank, and the possible causes could be due to the leakage on the tank wall, leakage of the pipe, and the flow rate indicator malfunction. While the possible consequences are less hydrolysis reaction, thus lead to less product yield, and for the action required, regular inspection to install low flow alarm and to install flow rate regulator. Same thing goes to the guideworks of no and more. The deviation, possible causes, possible consequences, and action taken are discussed. And same thing goes to the parameters of temperature, pressure, and level. And next, for the plant layout. Plant layout can be separated into 2 main parts, which are the top part will be processing areas, and the bottom part is non-processing areas. For the processing areas, the heat exchangers are to be separated from all the other units. This is because heat exchangers involving the processes of either very high temperature or low temperature. And these temperatures, let's say very high temperature processes, if we put all the units surrounding the heat exchangers, the temperatures of all the surrounding units will be bring out by the very high temperatures process of heat exchangers, and vice versa. And for the non-processing unit, the medical unit, control room, and the HSC department are placed near to the processing unit, because when there's an accident or any emergency cases happen, this medical unit, control room, and HSC department can be the first response team to the accident happen. While the assembly point is placed further away from the processing unit, because when something happens, all the staff and personnel are to be expected to assemble at this point, which should be far away from the processing unit, which means far away from the dangerous and any hazards. So that will be all from me. Thank you.
In conclusion, we have decided to locate our plant in Bukit Mentajam, Penang based on several factors such as raw material availability, water supply, market, and etc. Generally, to produce biogas from pomace, our feed will undergo 4 main digestion stages, which are hydrolysis, acidogenesis, acetogenesis, and methanation. Based on mass balance calculation, we obtain high production of methane and carbon dioxide, which mainly indicate our high production efficiency. Based on our economic potential, we obtain a total of 61 million ringgit per year. However, taking consideration of utilities cost, we obtain a total of 29 million ringgit per year, which indicate our process design obtain high profit value per year. Next, based on our studies in heat integration of our process, we have decided to replace 3 heaters with 3 heat exchangers to utilize our energy consumption. Lastly, our plant design had decided to include 13 controllers together with hazard studies, mainly at major and minor equipment, in order to maintain our process in control. So that's all from us. Thank you.